I actually included, this is still a population example, and then the second example is where we talk about radioactive decay or exponential decay. But I gave this example because you have a table of data. So understanding how to work with these models if you're given a table. So the table that's given gives the population of the United States in millions for the years 1900 to 2000. So we are going to use the exponential model, and just to remind you of what this means, the exponential model is the P of t is equal to P sub 0 times e to the kt. So every problem in this section with the way it's given, and I know things might be worded less or may seem to give less information in this section because they expect in this section you know what models to use versus if it was just a randomly worded question on the AP test, they would give you more information about what this meant. But so the exponential model, this is what they're talking about, that model that we talked about for exponential growth and decay examples applied to population here. So we're using this model and the census figures for 1980 and 1990 to predict the population in 2000. They do give the population in 2000, so the predicting in 2000 is to see how accurate the model is, to see how accurate it is to actually getting 275 million for the population. It's having us compare, and then we're going to use the model to predict the population in years 2010 and 2020. And I left 2010 in there because I know we already passed 2010. But we could then even look to see what the actual population was in 2010 and see how close that approximation was. 2020, haven't been there yet, so we could predict based on this model what that would be. But how to work through this if you are just given a table. Remember how we talked about on Monday or when you have a function like this, what we need to know is P sub 0, the initial population. We need a value for that. And then we also need to know K. And here we're not given the value that we would substitute in for either place, so we need to find what those values would be. So if we're using the figures for 1980 and 1990, we are then letting the population in 1980 be the initial population, be our P sub 0. So starting with 1980, that means we're going to let P sub 0 be 227, and again, it's measured in millions, but 227. So I'm going to substitute that in. So P of t equals 227 e to the kt. And then ideas on how we could find k. What did you say? Well, we have, so we're also given to use the figures from 1990. Okay, so if we use the 250 as the population value, what would we be substituting in for t? 10. Okay, so this would mean P of 10 is 250. And yes, so then we can, usually to find K, you need the initial amount, or you need something to put in place of the initial amount, and then you need another ordered pair that you can use to substitute in so you can find your K value. So if I substitute that in, and I'm going to write the equals 250 on the other side, so I'd have 227 times e to the k times 10 equals 250, and solve for k. So I would have to divide by 227. So e to the 10k is equal to, I'm going to leave this as is. Just to keep that value exact. And then I would have to do what to solve for k? Natural log of each side. So 10k is equal to the natural log of 250 over 227. And then divide by 10. So this is the exact value of k. Now what you could do, so that you don't have to then type this in, or type this in later using it in your function, is you could store that value on your calculator. So actually, I mean, calculate what this would be, natural log of 250 divided by 227 divided by 10. So type that in, and then again, to store a value, it's above the on key STO. You would just hit store, and then you choose which letter you want to store it as. So I could even call it K. So I would hit alpha, and then K is above that left parenthesis. But you would store it as whatever value you wanted to, and then just hit enter. So now anytime I type in K into my calculator, until I store over it, I'm going to get that value. Okay, so remember, when you're allowed to use your calculator, you can do that because you don't want to round anything until your final answer. Do not round in the middle of a problem. Okay, so then that also means if I have this listed as K, now if I'm trying to predict, it first says predict the population in 2000 just to see how accurate our model is, to see how close to 275 we get. So if I say in the year 2000, and I'm using this model I got here because I found my K value, in 2000, what's the T value? T value would be 20. So then I would be finding P of 20. And so this is just AP information I could write out to show what I'm calculating. I'm doing 227 times E. I can leave this written as K because I said right here what K is equal to. So it shows I found K. So I can leave this as K as long as in my work I've shown what K is. So E to the 20K. And I'll type that in and see how close we get to 275. Pretty close, 275.330 million. Okay, so that shows it's pretty accurate. I mean, estimating the year 2000 using the years 1980 and 1990, they're close enough that that prediction, I mean, it should be pretty close. That makes sense. It then also says to predict the population in the years 2010 and 2020. Because where this problem was from, it hadn't been 2010 yet. So there you go. What would T be in 2010? 30. But we can actually see how close this was. So 2010, I'm getting about 303.227 million. And then we can find in 2020. So in 2020, T would be 40. Did you have what that is already, Jake? 951. Okay. Anybody have your phone that you can Google what the U.S. population was in 2010?
I'll look it up.
We don't know what the population was in 2020, Jake.
Wow, they were way off.
309.3. So this was the actual. Okay. I'm curious though. So let's take the year closest to us. So let's say 2017. I'm just curious. It doesn't seem as accurate in 2010. If we estimated in 2017, the t-value would have been 37. So if I estimate this, so 324.420 in 2017. Liz, can you look up what it actually was last year in 2017? For last year, there wouldn't be? Oh, what'd you say?
Oh my God.
I sense not 325. Well, at least Google is giving us an answer. So just because, again, this problem, obviously based on the data in the table, I had gotten this problem from the textbook. Textbook's old. I was just curious, since we have surpassed 2010, how well that actually applied. But we can get an estimation for 2020. See how close that'll be once we get there. What? In 2020, you're not going to go back to this and check?
I'm not going to have this by mistake.
Thanks, Jake.
Like, no, but like,
no, I know. It's
I'll
fine.
hold your memory.
It's fine. It's
this
fine.
stuff is straight fire.
Okay, so just in general, with any model like this, you're looking again for that initial amount or something to put in place of that initial amount, another value that you can substitute in to find K. But are there any questions on that type of problem?
No,
I included it because of the table, just working through that a little differently.
That was easy, but this next one,
from the information we were given. The last example I have then, I just have as an introduction, so exponential decay. Working through these problems that deal with radioactive decay really isn't different. And just some information to start to show why we have the same model we did for population growth or exponential growth. So it says radioactive substances decay by spontaneously emitting radiation. So here it's talking about the mass of a substance. So if m of t is the mass remaining from an initial mass, m sub 0, of the substance after time t, then the relative decay rate is considered to be constant. And it actually gives, I just didn't type it on here, a formula to calculate relative decay rate, which you're going to notice is very similar to the relative growth rate formula we had for population growth. So it's negative 1 over m, again, m is the mass remaining, times dm dt, that first derivative of the mass with respect to time. So because the mass is decreasing if the substance is decaying, this dm dt, that derivative, is negative because the mass is going to be decreasing. And then because, or rather this negative sign is here, If these are both negative because the relative decay rate, they talk about as a positive value. But then because of this is kind of just putting it together to show why we have a similar setup. If I actually set this equal to some constant k, then I could rearrange it to have this differential equation. dm dt is equal to k times m. But because of this negative sign, what would be happening here is in this equation, this k would actually be negative because the mass has to be a positive amount. And then this is negative, meaning rather than writing negative k, they just consider k to be a negative constant. Okay, but because we have this type of differential equation where the rate of decrease, the rate of decay is proportional to the amount of the mass, therefore the solution to this differential equation would be of this form. M of t would equal the initial mass, m sub 0, times e to the kt. Yep, same setup. So any differential equation that's in this form will always have a solution in this form. So population growth, or that exponential growth, radioactive decay, which is exponential decay, even though they're just using different variables for what is being represented. Population was P, mass is M. The differential equation and the solution, same setup. Yes?
Well, for decay, how do you get it so that as t
But the substance, though, is decaying, so the mass would be decreasing.
Okay.
So that's why this first derivative,
Okay, is negative.
yeah, this first derivative would be negative because the mass is decreasing. Meaning, since this mass here is positive, rather than writing negative k, k is a negative constant. So yes, k for exponential decay, your k value will always be negative. So for this example, we have bismuth-210 has a half-life of 5 days, 5.0 days. So it says a sample for part A. A sample originally has a mass of 800 milligrams. Find a formula for the mass remaining after T days. So this is asking us to find the function m of t, which we have that form up here. So working through this is like what we just did. You need to know the initial mass. You need to be able to find the value of k in order to write your solution equation m of t. So I know the original mass was 800 milligrams, so that's the m sub 0 is 800. So I'll have m of t is equal to the initial mass, 800 times e to the kt. And then I need something else to substitute in so that I'm allowed to solve for k.
5 days.
Yes, after 5 days, this shows m of 5 would equal half of 800, so 400. So I know, and I'm going to rearrange this so I have equal to 400, so I know 800 e to the k times 5 is equal to 400. And then really what should always happen in this case, as long as you're using that first half-life amount, is now when I divide by 800, I'm always going to get e to the kt equal to the 1/2. But if you were using like the second half-life amount, like m of 10 equals 200, you get something different. So e to the 5k equals 1/2. And I will also show you some different ways this can be written.
Can we store it in a calculator to store positive?
Just store it as it is. So if it's negative, because your k value will be negative. to store it as negative. So if I take the natural log of each side, I get 5k is equal to the natural log of 1/2, and then divide by 5. K is natural log of 1/2 divided by 5. Now, like I said, I'm going to show you some different ways to write some things. Usually, you won't see natural log of 1/2 ever left as natural log of 1/2. Because I can write the natural log of a fraction or of a quotient as what? Like, what's another way I could write
natural log of 1 minus
Yes, natural log of 1 minus natural log of 2. Why would you do that? What is the natural log of 1? 0. So k is really, this is showing that k is negative. K is negative natural log of 2 divided by 5. Okay? So I'm going to show you this. I'm going to leave k written this way. So now if I substitute, because my answer is the actual equation, I'm going to substitute this value in for k. And I'll show you some different ways to actually write the solution. So we have m of t is equal to 800 times e to the negative natural log of 2 over 5 times t. This would be one way to write the solution to this problem. It is correct. It is fine. If this is a multiple choice question, you would not see that as an answer option. Or if you're working on this practice and you're checking in the back of the book, the answer will not be written like this. So this is for you to know how to simplify this. We know that e to the natural log, that cancels out. But it doesn't just cancel out the way that this is written. So what I'd actually have to do here to rearrange this is say I have 800. I'd have to split apart this exponent. So I'd want it to be just the e to the natural log of 2. And that means the negative over 5 and the t, this would be raised to the negative t over 5. So because that's all a product of two exponents, I am allowed to do this, because if I multiplied these, I would just get back to this. I just rearranged it. But then this e and natural log would cancel. So I would have 800 times 2 to the negative t over 5. And that would be m of t. You can't what? Like to the 8? Yes, that's correct. Yes, do not multiply the 2 and the 8. So this would be how it would be written. Yes. Well, if they were just asking for this equation, yes. Yeah. But you will need a calculator for parts B and C. They wouldn't ask these questions for no calculator. Any questions on coming up with this? Because this is the newer part. These questions, if I had given you this formula, you could have been asked these questions last year in trig pre-calc. So find the mass remaining after 30 days. How do you do that? Plug in 30. This exact one? Maybe. We did these types of problems in chapter 1. We set them up. We set up equations just like this using exponential models instead of using calculus to do it. So it's possible that we saw like this example way back in chapter 1. Did you say you already had this value, Quinn? 12.5 milligrams. And then when is the mass reduced to 1 milligram? How do we find that? Set it equal to 1 sol for T. And like we talked about on Monday, I know this came up, whenever you have to solve something like this, you'd be asked, well, I suppose you could be asked to solve something like this on a non-calculator part, and it would force you to leave the answer in exact form. If it was on a calculator part, you could graph this too and find the solution that way. But to solve this, I'd have to divide by 800. So I'd have 2 to the negative t over 5 equals 1/800th.
Wow, so small.
And then you could take the natural log of each side, really the log of any base, just to bring the exponent down. If you did log base 2 of each side, it would actually cancel out the 2. So I have negative t over 5 times the natural log of 2 equals, and what I'm actually going to do here, not that you'd have to do this, just like the natural log of 1/2 was negative natural log of 2, or the opposite natural log of 2, natural log of 1/800 is really the opposite or negative natural log of 800. Just because the natural log of 1 is that 0 minus the natural log of 800. So you wouldn't have to do that. I'm just showing you that again. So then divide by the natural log of 2. I could also say both sides are negative right now. So that really means if I divide each side by negative 1, can change into positive, multiply by 5. So t as an exact answer would be 5 times natural log of 800 divided by natural log of 2. You cannot. No. So whenever you have a natural log divided by another natural log, there is not a property to simplify that. This is not the natural log of 400.
Yeah, it's just 400.
The natural log.
Right?
No. Like, oh, if I just had 5 on the bottom. I mean, you could think of that as being a 1/5 in front, and so you could raise it to the exponent of 1/5, which would really be the 5th root. So yeah, I guess you could do that. And then what did you say this was? 48.19. And then it would be days.